Hello, this is Lab 5. I'm Andrew Johnson.
And I'm Matthew Stluka.
And this is part 1. So with the given Fourier series, we plug that into Simulink here by using constant and for now just the 3 sine waves. This was to represent the 3 harmonics for now. So we use the first, third, and fifth harmonic. And so we did this to test it, and so when we ran it and got the graph, we measured M1, M2, and M3. And with M1, this was where the signal intersects the t-axis for the first time, which should be close to, ideally it would be pi over 2 or 1.57. So starting out with just 3 harmonics, it was 1.89. And by the time we got to 9 harmonics, it was 1.678, which was showing a downwards trend towards pi over 2. So the more harmonics that would be added, the less error there would be. So then with M2, that was the value of change in t between the first and second positive peaks of the signals. So with 3 harmonics, it was 1.05. And by the time we got to 9 harmonics, it was 0.350. And so looking at the Gibbs phenomenon, the more harmonics that are added, it should compress and get closer together. And all of our data checked out and was showing positive output. And then with M3, which was the time at which the signal first intersects with amplitude of y equals 1. So this value should be close to 1.5 times pi, which is 4.7. And so with 3 harmonics, we had just over 5.031. And by the time we got to 9, it was 4.819, which is showing a trend towards 4.7.
In part 2, we analyzed a signal using frequency domain. We did this by combining two sine wave signal blocks and a random source block through an add block into a spectrum analyzer. The block parameters were set to the values that were given to us in Table 3 of the Lab 5 handout. And in the first part, we set sine wave block 1 to 5 kilohertz and sine wave block 2's frequency to a 10 kilohertz. When we ran the simulation and did the output, we saw that we had 4 main spikes in the signals, and these line up with plus and minus 5 kilohertz and plus and minus 10 kilohertz, which actually matches the minus and plus omega c's, because those happen to be the frequencies. So they line up with both sine waves frequencies. Then in the second half of this, we actually changed the sine wave block 2 to have a 5050 hertz frequency, and when we ran it, it looked like you could see only 2 main spikes, which is kind of an optical illusion since there's really 4 at plus and minus 5 kilohertz and plus and minus 5050 hertz. So if you zoom way in on the actual output, you can see a slightly offset spike at both those locations. So there's still technically 4 spikes, but visually overall looks like there's only 2.
So for part 3, we took the audio file given to us on Canvas and put it into through a spectrum analysis analyzer, and from there we viewed the output of it, and then we also took mine and Matthew's voices and did the same. So after all 3 were ran, we took the captured images and compared them and noticed somewhat of the same trend, where the pre-recorded one starts kind of low and starts rising and then ends up to a peak and then goes back down. Mine does that also, but it doesn't have the peak. And Matthews has the peak, but doesn't start very low. It doesn't rise as quick. It rises exponentially to the peak and then decays exponentially.
The discrete Fourier transform.
The discrete Fourier